Welcome to the third lecture of EE298, Generalized Principal Component Analysis. So let's start the lecture this time for a brief overview of what we have learned last time. So last time we talked about two problems. The first one is how to determine an optimal number of principal components, that is small d. And we also talked about a new formulation for PCA called Probabilistic PCA. So just let's go through the derivation very quick. So we know that for choosing optimal number of principal components, if we assume moderate Gaussian noise, the problem becomes a model selection problem. So nonetheless, we can still find a trade-off between model complexity and the data fidelity. A simple example is to minimize this objective function, which consists of two terms. The first term represents the data infidelity, which is the sum from d plus 1 to capital D, a number of sigma square, which is the singular values of the covariance matrix, singular values of the data. And the second term is the a approximation of the model complexity. In this example, we just use the dimension of the subspace as a rough approximation of the complexity. Okay. And we also talk about the probabilistic PCA, and the approach assumes that observations x are generated by this equation, three terms. The first term is the mean vector, and the second term consists of a representation of the basis ud and random variables y and epsilon. Okay? Now, if we can simplify the probabilistic model for the random variables y to be standard normal and the noise epsilon to be isotropic, then we can write down the estimate for the mean vector is equal to mu x, and the sigma, the covariance matrix is equal to ud times ud transpose plus sigma squared times the identity matrix. Okay? And therefore, we can also write down each observation also as a Gaussian distribution in capital D dimensional space. And the next, what do we do? After we have this distribution, now we know that in practice we have n samples. So we are going to compute the log likelihood function like this. And then we are going to take the gradient of this log likelihood function and set it equal to 0. And we get the condition to find the stationary point of our solution. And of course, after you find a stationary point, you also have to verify if this is a minimum or a maximum. Nonetheless, after some derivation we went through last time, and we get two closed form solutions for the estimation of the basis of the subspace ud, and also the estimation for sigma square. Okay, so that's what we discussed last time. And we have also started this topic called Kernel PCA. Let's continue our discussion and try to finish for the first part of this lecture. And then in the second part, Professor Sastry will take over and start the new chapter, Generalized Principal Component Analysis. So if you assume that your data is nonlinear in this case, then what the nonlinear mapping does is hope that you can find a nonlinear map phi that maps your sample from capital D dimensional space to an m dimensional space, okay? Such that after the embedding, the structure becomes linear. After that, you can just use PCA, apply to the embedded space, and try to find the linear subspace model, okay? And we have seen this very simple example. And using this example, we define a very special embedding function called the Veronese embedding. So can anybody remember what is the definition of a Veronese embedding? They are a list of monomials. So here's the definition. So the nth order of Veronese embedding in the d-dimensional space is the list of nth degree monomials in d-dimensional space. And we have also discussed how to compute the dimension of the Veronese map, which is equivalent to the famous n-ball d-cell problem. So at the end, we get this, this quantity, which is n plus d minus 1 choose n d minus 1. Okay? So the problem is that oftentimes when capital D and n are large, this dimension blows up after you do the embedding, mapping samples from probably already high dimensional space onto an even higher dimensional space. So the question we want to solve for kernel PCA and nonlinear PCA is that can we find the higher order nonlinear structure without explicitly calling the embedding function? So that's what we are going to talk about today. Okay, so this is nonlinear PCA. So in this case, first we can assume that we can compute phi bar, which is the sample mean in the higher dimensional space after the embedding. And we can remove the mean from my data matrix like the following. This is capital phi matrix. By the way, what's the dimension for capital phi? Can anybody just figure out very quick? Remember, what's the dimension for after the embedding? What's the dimension for the embedded space? What we say is n, right? So what's the dimension for this matrix when you have n samples? So let's write it down. And it's important to keep track of the dimension because later on we are going to do some computation. So this capital phi has to be in the dimension of n times n, right? After embedding, each column is the m dimensional vector, and then you have n copies, n samples. Okay. Then we can compute the nonlinear principal axis in the embedded high dimensional space, which is equal to the eigenvectors vi of this covariance matrix, right? So this is true regardless you are in the lower dimensional space, in the original ambient dimensional space. That's the definition for a standard principal component analysis. Or in the embedded space, you still get this result, right? And also, the nonlinear principal component is also a projection of your sample. Now is in the embedded space. After you remove the mean, projected onto the corresponding principal axis. So this is true in the ambient space. This is also true in the embedded space. Okay. So next, we are going to show the following result. That
Did you point out that m is at n plus d minus 1 choose?
m is general in general. So
But phi is m here.
oh, in this case, phi doesn't necessarily mean the Veronese embedding. The Veronese embedding is just a special case. So let's just see this result. So we're going to say that the eigenvector and eigenvalues, the eigenvalues of phi transpose are the same as those of the matrix of phi transpose phi. So without proving this at first, let's just consider why this is important. The reason is because why I need to write down the dimension of phi over there, because if you keep track of dimension, phi transpose is of dimension m times m. And on the other hand, phi transpose times phi is equal to n times n. Okay? So as the title says, in the case that after the embedding, m is much larger than n, solving an eigenvalue problem with respect to phi transpose phi is much more efficient than solving phi transpose, right? You have a smaller size of your matrix to solve. In here, you have a much larger size of the matrix to solve. Okay? So that's the reason. If this is true, it's going to help us tremendously in nonlinear PCA. So why this is true? Okay. So let's first prove the first one. So first, let's suppose V is an eigenvector of phi transpose with corresponding eigenvalue lambda. In this case, it means nothing but phi transpose v equal to lambda of v, right? So you multiply both sides by phi transpose, and then you get this equation, okay? And you treat this one as a new vector. You treat this one as a new vector, and you can define. And so, which means phi transpose v is an eigenvector of phi transpose phi, and lambda is the eigenvalue. Okay? So this is the first one. Now let's look at the second one, the other direction. Now let's suppose now W is an eigenvector of phi transpose phi. And we know by definition that then, which means phi transpose phi W equal to lambda W. Okay? And which means phi transpose phi W equal to lambda phi W. Okay? So which the same argument, same as the right. And now we can see what is V, which means let V equal to phi times W, then it means phi transpose V equal to lambda V. Okay? So that's what we have. Okay? So let's wrap everything together. So it means, let's go to the very beginning. It says, in the case the n is much larger than n, computing the eigenvalue problem of this guy will be much easier than computing the eigenvalue of this guy. What I can do is that I can compute the eigenvalue and eigenvector of this guy, and I get lambda and W, right? And from this equation, I can recover the corresponding eigenvector of the same eigenvalue with respect to this guy. Nonetheless, this guy is more difficult, more expensive to compute. So I avoid computing the eigenvalue problem on this guy by resorting on this guy.
Just to pick you on this, so phi transpose has got capital N eigenvalues, and phi transpose phi has got n eigenvalues. The numbers are different. So clearly, so what are the ones which are not listed? The ones which are not listed. Same Of course, you know the rank of phi transpose phi, or phi transpose phi is the minimum of m or n. Right? And so that the discrepancy between the two numbers are zero eigenvalues.
So the description between solving the two eigenvalue problems, because they have different dimensions, are all zero. Okay. So the conclusion is that now, based on this observation, that computations in the nonlinear PCA only involve inner products of the embedded samples, not the sample themselves. So what we can do is that the mapping relation can be expressed directly during the computation of PCA without explicitly writing down the embedding function. What we do need is a new definition called the kernel function, which is defined as the inner product of two embedded samples. Okay? So here's the definition. So the kernel function is a positive semi-definite function equal to the dot product of phi of x times phi of y. Okay? And using this positive semi-definite function, we can define the corresponding positive semi-definite matrix called a kernel matrix. The element of Kij is simply the value of k of xi, xj. Okay? So there's a relationship between the positive semi-definite function and the corresponding positive semi-definite matrix in here. So that's the definition. So next, we are going to see that why this is true. So given this definition, let's just see if we can compute the nonlinear covariance matrix, which is in n by n. Remember, we want to, previously we said that we can replace the computation of computing the eigenvalue problem of phi transpose as a more efficient one. So this is the guy of dimension n times n. Let's see how to compute this matrix from the kernel matrix. So what I can do is to investigate how to compute the elements of this matrix. So the element of this matrix, actually, I don't think that I need to write it down. Okay, so the element of matrix is equal to this vector times this vector, right? The normalized version of phi of xi and phi of xj, the dot product between the two, and then if you multiply the 4 terms, and then you get these 4 terms. Okay? Phi bar is the mean of. So now you see that it's an average of this. So phi bar is equal to an average of okay. So now, how to derive from this step to this step? So what we only need to do is to check if the element-wise, these two matrices are equal to each other. So what you can do is, let's say k, the left-hand side, equal to k1 plus minus. It's easy. We don't have to check the sign. Let's just make sure that we have the right sign. Minus k3 plus k4. Okay, so it's easy to see that the first term is equal to this guy, right? So k1 is nothing but kij, right? So next, I'm going to only verify one term. For example, this term. So you can go ahead and verify the other terms. Now let's see. What is n 1 over n k? This is a 1 vector times a 1 vector transpose. So equal to 1 over n. This is just a constant, but let's just carry it throughout the derivation. So what's this term? This term is k times a 1 vector. It gives you a vector, right? So this one will give you the sum of the first row of k, right? So this gives you one to n k1 I, right? The sum of the first row of the K matrix. And what's the next one? The next one is the same. K2I. And The last one is KNI. K. Yep. Let's see. Yep. And this guy is going to be continue times 1 transpose.
K transpose. The 1 transpose is the matrix, right? The 1 times 1 transpose is the matrix, right?
Yes, but I'm computing this guy. Yes, this will give you a matrix.
1 is a vector.
No, K is a matrix. K is defined as the following. So if you multiply this guy, you are going to see you get back a matrix which give you, for the first row, it's going to repeat everything. It's going to be the same. So I'm going to not write the dummy variable. And KNI. So you check, that's exactly what you get from here. So which means Kij is equal to an element in here for this part. You can see? Which means K, for example, if I equal to 1, K1j for all the rows of this component is going to be the same. And it's equal to K1j. Okay? You can verify this, the same relationship by the similar fashion of the third term and the fourth term. Okay? So the conclusion is after we get hold of this K, what we need to do next? What do we do next? So let's, again, go all the way back. We start with n samples and assume that we have definition for kernel matrix. For the kernel function, based on the kernel function, we can get hold of a kernel matrix, so-called kernel matrix, by the definition of the kernel function. Then from this equation, I get a representation. I get a representation of my nonlinear covariance matrix K as some manipulation of the kernel matrix. And what's the next step? Yes?
Sorry, what do you mean by nonlinear covariance matrix as opposed to this covariance matrix?
Oh, in here, nonlinear covariance matrix means the covariance matrix after nonlinear embedding.
So the covariance matrix of the data which you have now, like in the entitlement.
After the embedding, yes. Yeah.
So the matrix is not nonlinear.
No, no. So what do we do next? Compute the eigenvector and eigenvalue of this guy. Right? So the next is compute W and lambda of K equal to phi transpose phi. We get back to the previous slide. Why? Because we want to compute the nonlinear eigenvalues, nonlinear principal components. We know that this guy is equal to W, phi times W, right? So after we get hold of this guy, we compute W and lambda. From there, I can recover this part, exactly as this equation tells you. Okay? So this is what I want to compute. And from the previous slide, after the derivation, and after I compute the eigenvalues of the so-called nonlinear covariance matrix, I get all the W. From this equation, I get V. Okay? Now this component, this part, is now solved. The only thing that is standing in front of us before we can compute the eigenvalue in high-dimensional space is this part. Okay? So the last part is to derive, can we derive this part also only based on the kernel matrix. If we can do that, then all the steps that we need to compute the nonlinear principal values, principal axis are all from the kernel matrices. We don't need to write down the definition and also do the computation based on the nonlinear map function anymore. So this is the last part. Again, let's look at this. Let's look at this vector element-wise. So the ith element of this guy, phi matrix transpose times the normalized version of the embedded sample x. Oops. Small case bar I is nothing but the embedded version of the xi sample times the new sample x. Right? And you multiply the 4 terms separately. It's equal to 1, 2, 3, 4. Okay? And so it's equal to k of xi x minus 1 over n sum of kil of L minus 1 over n k x h x h plus 1 over n squared hl khl. Okay? So next, so we're going to define kx, that is this term. Basically, you can guess what I'm driving at. Is trying to get hold of all the elements of this part. Define this one equal to kx1x kxnx. And then this vector is equal to the right-hand side. You can also similarly check using the technique that we have just discussed. Okay? Any questions? So after that, you can see that during the process of computing an eigenvalue in the higher dimensional embedded space, the entire computation is converted based on the kernel function and the kernel matrix. So we completely eliminate the need to call the embedded function during the computation. So that is the gist of the kernel PCA method. Okay? So finally, just remind you some of the popular kernels that you are going to see in the literature. We have polynomial kernels, and then the Veronese embedding will be, okay, so that we have polynomial kernels. And some people also often you are going to see the Gaussian kernel or the radial basis function defined like the following. And in the image-based object recognition, people always also like to use the so-called intersection kernel, which is defined like the following. So you have two vectors, the intersection kernel, when the coefficient of those vectors are non-negative, is the minimum value of those coefficients. Okay? Yes?
Originally, we started with the kernel function being the inner product
Yes.
that you have to feed in there.
Right there. Yes.
So, but then, and now you're saying K can be in with each other, like the design choice or something?
Oh, phi is also the design choice. I mean, for every phi, you have corresponding K, right? What I'm saying is that this is the definition. So from there, so you can, after you have the definition for K, if you can write the K explicitly, then you don't have to write down what is phi anymore. If you know at the end K is equal to this function, then you don't care about phi anymore because the entire computation is converted into the computation of the kernel function and kernel matrices. So you don't have to use phi anymore. Of course, if you don't know K, you only know phi, the definition of K is based on phi. But in practice, if you know what you're going to use in terms of the kernel function, and there are several very popular choices. So in that assumption, then you don't have to use phi when you compute the nonlinear principal axis and principal values. Okay?
So that particular kernel function you started out with is for the Veronese mapping in particular?
This function,
No, the first one you showed us. Yeah. The one.
this is general enough. This is for any phi. This is for any embedded function. Yeah.
Well, so this is actually the question. Oh, well, I was supposed to talk. Look, I think the issue is not every positive definite symmetric function can be factored separately as a function of x and y. So in that sense, if you chose a phi, kxy is written as phi x transpose times phi y. But I think that all the examples that he put up on the next slide were actually separable. In that you could write that, I think they're all separable. Is the Gaussian kernel a separable? I don't know exactly how you break it up as phi x transpose phi y. So, so in some places in the literature, instead of specifying exactly what this phi is, people just specify k. And I think the point to some of these calculations was to show that, you know, if you just knew this function k, you can still derive the principal components by operating on this matrix k, which comes from phi xi, phi xj, and then, you know, this vector of ones. And, you know, I mean, actually, I have to tell you, you know, a lot of this chaos is just caused by the fact that they're not zero mean. If things were zero mean, you know, all those other terms are zero. See, the kappa equals k if there was no phi bar, if phi bar was zero. So if you sort of did phi of x and then assumed it to be normalized, you won't have all this chaos with 1-1 transpose and so on and so forth. So, you know, so some of this is really somewhat cosmetic for, yeah, the mathematical reason why one would want to deal with this kxy is there's a theorem called Mercer's theorem, which tells you how to decompose arbitrary positive definite kernels and so on and so forth. And that's in the book. I guess you decided not to cover it. Yeah, so at heart, you know, phi is an attempt at trying to linearize a problem that was otherwise nonlinear, and then after that, it's singular value decomposition of k. And the first, the biggest principal components of k are the nonlinear kernel PCA, and that's why it's called Kernel PCA. Oh, am I starting? Okay, look, I think that, you know, as we go, I think it's better to do the proofs on a board. So I'm, by and large, going to be working on a whiteboard, except today I thought since Alan was going to do PowerPoint, I try to give you a little bit of an overview of what Chapter 2 and Chapter 3 look like. I think Alan sent out now not just the early chapters, but sort of a draft of the manuscript. That's now, you sent this out, right, to the...
I sent the first 3 chapters.
Of this.
I still have to work on the rest.
Yeah. You know, the references, of course, are there. It's still a work in progress, but at least this is the May 20th edition rather than the March 20th version, which is what you had before. So, I asked myself for wireless widgets. Thanks. what Alan told you also, so some versions of this class have been, I taught a version of this in Stockholm in the spring, and I think Rene Vidal was teaching a version of it at Johns Hopkins, so that's the story. This will be posted on the web. I don't think it's posted yet. The heart of the class is really sort of chapter 3, and then of course the application chapters that follow. So rather than, I'll do most of chapter 3 on the board starting next term, because I think these proofs are better appreciated by somebody deriving them on the board. But let me just sort of give you a preview of this. It will also serve as a little bit of a review of what you've seen from Alan in terms of principal component analysis. Principal component analysis is pretty old. It's, in terms of the history, even though it seems to have surfaced in the statistics literature and in the numerical linear algebra literature rather more recently, I think that certainly Gauss knew about principal component analysis, and even such authoritative sources as Wikipedia will tell you a history which goes back to the early part of the 19th century. So principal component analysis, of course, is if somebody gives you a bunch of points, how do you fit subspaces to it? And that's certainly what Alan's been talking to you about. And here's a summary of what he said. If somebody gives you capital N points, I know Alan's not a fan of capital N, so he's been using little n. And capital N is consistent with the book, so I will stick to it. If there are capital N dimensional points which are in RK is the ambient space, you stack them next to each other, make a k-dimensional matrix, and then you factor it as a singular value decomposition, U sigma V transpose. I think Alan showed you how to formulate an optimization problem to get the first singular value and then the second singular value and so on and so forth. This is k by k. This is n by n. Sigma is rectangular, but it is block diagonal in the sense that depending on whether k or n is bigger, there's a piece of sigma which is all zeros. And the non-zero entries of the diagonal part of sigma are called the singular values. And the story is this principal components is you take a look at those sigmas. Some of them are big and some of them are small. You set a threshold and say everything below the threshold is as good as non-existent, and the rest are called the principal components. And that's what the agenda of chapter 2 and the agenda of what Alan's been doing so far is. I think that that's quite a deterministic story. You're just given points, you form the singular value decomposition, you set a threshold epsilon, and of course, the numerical linear algebra guys love this because you're always taught about ranks of matrices, but the rank of a matrix, it's impossible to compute this because generically, because of numerical noise, all matrices are full rank. So the way you actually compute the rank is by saying all singular values below epsilon are as good as 0, and that's how you determine rank. That's called the numerical rank of a matrix. And the way you compute the numerical rank of the matrix is you set that threshold epsilon, and then the number of non-zero singular values that are bigger than epsilon, you call that the numerical rank. So that's a deterministic story. So in the statistics literature, these two guys, Tipping and Bishop, figured out that there was a probabilistic interpretation of this, and I think, again, Alan's gone through this. It says that if there is Gaussian noise on top of some elements, instead of they're lying on a subspace, the deviations from that subspace correspond to, the small singular values. And so, in effect, throwing away the smallest components has the effect of throwing away the noise. and you set that threshold epsilon based on your estimate of the variance of the noise, so as to throw things away. What you just heard from Alan was these things which are known as Kernel PCA or Nonlinear PCA. The names that one associates with that are these three guys, Sholkoff, Smaller, and Muller. And what they're trying to do, and what Alan was trying to do in this phi and phi transpose, etc., was if there's data which, you could say that data doesn't lie on subspaces, it lies on manifolds. And what's the simplest thing you can do if you were to try to fit things by manifolds? You try to get something which is a linear parametrization of that manifold. And that linear parametrization, you have splines, or you have quadratics, or quartics, or cubics, or polynomials. Those are the candidates for this thing phi that Alan was talking about. And in effect, the linear parametrization, what it does is it takes this problem and converts it to a PCA problem. And of course, issues arise as to what embeddings are optimal. Are splines a good idea? Are polynomials a good idea? Are sines and cosines a good idea? Etc. And those are all open problems. So that's the agenda of Chapter 2 was to actually review this in somewhat great detail. And, I think that in the case of the probabilistic PCA, how you form these matrices, how you determine what the covariance is, empirical covariance matrices, all of that was what got covered. Now, our starting point really was to think about what are called mixtures of models. Quite often you're given data which neither belongs to a sense of its being data on a subspace plus noise, nor data lying on a manifold, but really data which looks like this. Now the problem is we are given data that looks like this, it's just like these black points and yellow points, and nobody has told you which points are black and yellow. If you were to try to do principal component analysis, what would happen is that you'd get a subspace which sort of goes down the middle, and it would be a terrible fit for all the points. But, if you insisted on a single subspace, that's what principal component analysis does. On the other hand, if you were asked to eyeball the data, you'd say, well, maybe there's one model here which corresponds with some of these points ought to be labeled yellow. The other points ought to be labeled black. And once you've segmented the data into these two sides, you can fit the two sides by different subspaces. And this is called, it's called a mixed number of things in the statistics literature. It's called mixtures of PCA. It's called mixture because somehow there's a Gaussian distribution with with its covariance along these principal components. There's another Gaussian distribution corresponding to points that are here, and then you have a convex combination of those two distributions. So that is one reason it's called mixture. Other way, people call it multi-model because, presumably then you say some of the data corresponds to one kind of a model, one kind of a behavior, and the other kinds of points correspond to a different behavior, a different model. And what you would like to do is to be able to, in addition to fitting the data, actually identify which model a subspace comes from. This is what we have called in this book generalized principal component analysis. And it's generalized in the sense that, it's a generalization to multiple models. The applications that certainly motivated us were a number that came from computer vision and image processing. This notion of vanishing points. If you look at a picture like that, that's the so-called calibrate. These are just horizontal and vertical lines. Even if lines are horizontal and vertical, when you take a picture of this through a perspective camera, there are several vanishing points, which is where otherwise parallel lines appear to meet. Right? For instance, all of these lines appear to meet. These are all supposed to be parallel, but they meet at some point up there. All of these lines will meet up there, and all the vertical lines also meet at some point. Now, the reason that one is interested in these are so-called vanishing points. Again, the history of using vanishing points is really quite old. Painters started discovering this as when they say that in the frescoes of Pompeii is when people first started painting vanishing points. They didn't have a very clear idea. They used to have too many vanishing points, and then it was all forgotten. And in fact, till the 13th century, all paintings look very flat because nobody had vanishing points. And it's only during the Renaissance that they rediscovered vanishing points. And by the time it came to Raphael in the 15th century, they had it down. But now, the reasons that you do this is if somebody shows you a picture, you'd like to determine these vanishing points to determine the location of the camera relative to the scene. That's called the calibration of the camera. And you want to do this because, in a lot of these applications, you walk around a scene and you take multiple pictures of that building, and the question is, how do you then do a flyby, and how do you sort of mosaic them? For instance, at Microsoft Research, they have a big project called Rome in a Day. Somebody who's gone and take thousands of pictures of Rome, and then how do you give somebody a tourist experience of how these pictures mosaic together so that you can fly through this. So that's the reason why you need these vanishing points. Other things are this image segmentation. Image segmentation is this notion of how do you break up an image into different regions. It's important to break up an image into different regions, partly because it's easier to analyze this image in pieces. It's really easy to compress these images when they're in pieces. When people talk about MPEGs and JPEGs and MPEG-5 and MPEG-4000, these are all ways of actually doing compression based on some way of breaking up the image into bite-sized pieces that you can encode, which is why it's a big piece of image compression. And that's why the first half of this book, chapters 1 through 5, are the theory, and chapters 6, 7, 8, 9 are applications to vision, compression, hybrid systems, etc., etc. So those are the kinds of places these things show up. And you can segment things based on color. Is black and white. This is a grayscale image. You might want to segment them based on, that's the intensity segmentation. You might want to segment them based on texture. This is sort of in this compression business, this the image that they use, the test image for testing all their compression algorithms, is this wonderful baboon. And the reason this baboon is because when you want to compress this baboon, you want to be able to separate the different textures on his cheeks, on his mustache and beard, and when you reconstruct it, the reconstruction schemes should not introduce so-called blockiness. When you're on the internet and you sometimes have images downloading, they start off blockier and then less blocky, and so that's how. So blocky means a bad compression, and less blocky means good compression. And that's why that's it. Another thing that people like to try out these segmentation algorithms is on animals. And the reason they do animals is because animals are quite often camouflaged. And so they're designed to fool the human eye or other animal eyes. So tigers have stripes, so they can be mistaken for leaves in a river, and so on and so forth. So when you do segmentation schemes, you apply them. Sometimes it's so-called motion segmentation. So for instance, here's somebody looking out the window of a window of a house, and you see a car drive by, and then you like to break it up into what parts of the scene are stationary. In this particular case, the camera actually jerks back to where it begins. If there are different objects moving at different speeds, you'd like to do that. Another thing to do is people are interested in this annotating video data. Annotating video data means like automatically generating some commentary by looking at the data. So this is not my favorite commentator, but if you take a look at this, you can see that there are pieces where the interviewer are looking right, left, Karen Hughes on one side and Karen Hughes on the other side. And they presumably correspond in some cases to the host changing what he's saying, but in the other case it's switching the camera, switching from the host to the guest, and so on and so forth. If you have audio which is associated with this, you have a transcription of the audio, and it can all be a way to provide commentary. You can think that there were some folks in the media lab who thought that they'd produce automatic football commentary, like just watch an NFL game, for instance, the playoffs, and come up with, explanations of what might be happening. And that, I think it's still quite interesting. The reason we didn't have a class on Tuesday, we had this research review, and in that there was people talking about looking at a soccer game and trying to figure out strategies. So those are the reasons why you might care about this. Alan's claim to fame is that, the Homeland Security and all kinds of other agencies use Alan's face recognition scheme. And his big thing is, what if people try to, a lot of these face recognition schemes, people try to fool them by wearing dark glasses and beards and growing facial hair and all kinds of things. And, it's our contention that it really shouldn't matter, if somebody wears dark glasses or obscures their eyes or wears a beard, because these images are very rich. And in fact, he has got a scheme based on this GPCA which enables you to, to deal with this kind of recognition. Other things are, this is a person with these markers on their joints. And the amazing thing is, even with this rather rudimentary information, you can make out lots of things about this. I mean, if I asked you, is this likely to be a man or a woman? And maybe I should ask you, is this likely, is it a man or a woman? And what can you tell about this person just from looking at these sort of these snapshots of what these are just LEDs, attached to the clothing in a dark room. So I think it's I think nobody is willing to take a guess.
Not so flashy.
Flashy, yeah. Most people are ready to bet that it's a man, and the man's limping, and those are both accurate. The reason it's flashy is because it comes to the end and it picks up, and then you can tell a fair amount about gaits from that. Other things are different kinds of textures. Here's a steam texture moving across a wave texture, and the question is, would you be fooled into thinking that the two textures are similar?
I think that's the thing with toilet sequence.
This is a toilet sequence?
Yeah.
All right. Good. And the other ones are, things which come out of ultrasound. Ultrasound images are notoriously noisy, but you'd still like to be able to, this I think is the heart of a fetus, the heart of a, a newborn, not yet born baby, and you'd like to be able to take a look at what it looks like. And the questions are, how do you do the analysis of this? Okay, so these are, I think, these are what lies ahead in terms of talking about the applications. So let's talk a little bit about what mathematics looks like. So the mathematics, amazingly, has also got a very long history. This is, the mathematician David Hilbert came up with a number of problems which he thought were the hardest problems in mathematics, called Hilbert's problems. And this problem of generalized principal component analysis is one of those. But amazingly, you can actually solve it. You can solve it, and I may not be, I don't know if our notion of having a solution, namely having an algorithm whose answer is the correct answer, would be completely acceptable to Hilbert. Hilbert couldn't be bothered by noise. He was really interested in exact solutions and algebraic geometric solutions. So this is really Hilbert's 16th problem. And so the issue is, if somebody gives you a lot of data, and we can start with a noise-free case and then sneak up in the noisy case later, how do you figure out how many subspaces, if you do know that they lie on an intersection of multiple subspaces, but you don't know how many there are, how do you figure out the number of subspaces, how do you figure out the dimensions of each of those subspaces, and how do you figure out a basis for each one of those subspaces. So you're now, instead of principal component analysis, you've got to break it up into M subspaces. You don't know how many, you don't know how many M is. You don't know the dimensions of those subspaces, and you don't know the basis for this. So that's what generalized principal component analysis is. And the issues, of course, and I think Alan had a pretty picture of a chicken and an egg and so on in one of his earlier slides. If you knew how to segment the data, if you knew which points were purple and which points were green, it would be a lot easier to just then do principal component analysis, and then the principal components would be not the basis for the subspace, but the normals to the subspace, and that'd be good enough. Yeah. Thanks. So, so we had a little bit of a discussion with Alan about whether I should have started with the prior work. There's a lot of literature in learning, and I think there are a number of classes on learning which actually talk about iterative ways of doing it. We'll review them next after we're done with principal component analysis, called k-means and expectation maximization and ransack and so on and so forth, which are iterative algorithms for solving these. And what I'd like to do is to actually show you a more geometric, so that, you know, there's certainly a issue of what do you do with noise and what do you do without noise. We'll start off with the noise-free case and then sneak back onto the noisy case. And in fact, after we're done with the algorithms, we'll make rather detailed comparison between k-means, expectation maximization, and generalized subspace, generalized principal component analysis. Okay, so let me just give you a preview, and then, as I said, I promised, you know, we'll do this all in on the board. You know, I'm going to redo what you see here on the board starting next week. So, how does an algebraic, and you know, it's called segmentation in GPCA because you got to segment the data and then fit it, right? And so the question is, how do you do them together? Can you do so analytically? Is there a formula for the number of models? And, you know, we're going to assume that the subspaces are of unknown and different dimension. Because they're subspaces, they only all go through the origin. That's one point that they have in common. Subspaces don't need to be orthogonal. You know, the statistics literature, they like subspaces to be orthogonal because that translates into being uncorrelated. So here we do allow for them to be correlated, uncorrelated. So in what follows, you'll see that the number of subspaces gets determined by the degree of a polynomial, which I'll show you how we compute. And the dimensions of the subspace actually come out, the basis elements come from differentiating a certain polynomial that we'll compute, differentiating that polynomial. And there's two different things, a polynomial fitting way of doing it and a polynomial differentiation way of doing it. That's what the subspace clustering comes out to be. Okay, so the algorithm, you know, the heart of the algorithm is actually quite simple. It does involve this Veronese map that Alan was talking about, but let's sort of sneak up on it by just thinking about how you might cluster points in one dimension, in R1. So if you have points that belong to, if there are two clusters in R1, if there is no noise, that means that it's either x equals b1 or x equals b2. That's what the description of these two clusters is. Even though, you know, we've shown the clusters as sort of separated, let's just say they all lie right on top of each other at b1 or b2. So, you know, this is what you say in words, x equals b1 or x equals b2. If you convert that to a formula, and or, you know, so x equals b1 is the same as x minus b1 equals 0, and x minus b2 equals 0 is x, so x equals b2 is x minus b2. And the or connective is a multiplication, right? Because if you say this is equal to 0 or this is equal to 0, it's good enough to say the product, because the product is 0 if either one of them is 0. That's why it's a x equals b1. So, you know, so that translates into the fact that, in fact, every point in this cluster should satisfy the quadratic formula x squared minus b1 plus b2x plus b1 times b2 equals 0. Okay? So that's easy stuff. If I write this down as a matrix, and the matrix separates the unknowns, presumably B1 and B2 are unknown, even though it's such a trivial example. You just see B1 and B2. Here's the data. Here are the unknowns. And and right now I say we have 2 clusters. Eventually we're going to say we don't know how many clusters, and so on and so forth. But the way you write it is, here's the data, here are the unknowns, equals 0. And you have one equation for every point. There's x1, x2, xn. There are n such points. So how do you stack those up? If there are capital N points, that corresponds to saying this is the data matrix. Is x1 squared, x1, 1, the point 1, point 2, and if there are n points, then each of them should have the same null space. So so immediately now, things start popping into your head. P is a n by 3 dimensional matrix. Why is it 3? Because, you've listed all the monomials of orders 0, 1, and 2. They're only monomials, right? It's the scalar variable is x1, x squared, and x to the power 0, which is 1. But, so this is this matrix P. So if you were given n points, you take a look at the rank of P. If the rank of P is so the rank of P had better be less than 3. If you have to have, unless the data is not clustered at all. But if the rank of P is equal, so what are the number of groups? It says if the rank of P is equal to 1, that means there's only one group. Which means, if you had just x equals B1, then you'd have had a null space. The equation would have been x minus B1 equals 0. And you'd have had a null space already corresponding to x minus B1. And you'd have a second null space corresponding to x minus 2B1 plus B1 squared. And so the rank of P would be, the rank deficiency would be 2. The rank of P would be equal to 1. That would be one group. If the rank of P is 2, there are 2 groups. So the rank deficiency of, so the rank of P tells you how many groups there are. So how do you convert this into an algorithm? So if you had m clusters, and you don't know how many little n clusters, and what you do is you don't know what n is, so you don't actually know how to form Pn. But what you do is, how do you compute n, the c's, and the b? And everybody understand this? So I said if you have n clusters, it's x minus b1 times x minus b2 times x minus bn. That's an nth order polynomial. You don't know the dimension n of the polynomial ahead of time. You're just given the data points. But this corresponds to the fact that Pn has got a dimension, null space of dimension 1. That means the rank of P is 1 less than, and if capital N is large, it is 1 less than n plus 1, so it's rank n. So how do you compute n, c, and then even if you compute the c's, the c's are not exactly the b's. The c's are all the relationship between the roots of the polynomial and the coefficients. The relationship between the c's and the b's are between the roots of the polynomial and the coefficients of the polynomial. So how do you recover all of this? So the way you convert this into an algorithm is you keep forming P1, P2, P3, and keep computing the ranks of Pi. The smallest step I, at which the rank of Pi becomes equal to I, gives you the number of clusters. That's the first time that the rank deficiency drops by 1 less, because Pi always has rank capital N times I plus 1. This is for capital N sufficiently large. You need enough data, or at least capital N should exceed I. That's what they should, and that's the number of points should exceed the number of clusters. Every cluster should have at least one member, so it's not a terribly different thing. So that tells you the number of clusters. So this Pi is the poor man's or the scalar version of a Veronese matrix. Pi is the Veronese matrix. It's only one variable of all monomials up to order I. And so the I at which it becomes the rank of this matrix, Pi becomes I, is where you stop. it's all noise free because, if there's noise, the rank of pi equals I, that doesn't, maybe it'll always stay I plus 1, so you'd have to have an epsilon rank. So it's not very computational. After you're done with this, once you have C, once you stop, you have a null space. Take the coefficient of the null space. That gives you the polynomial P. Compute the roots of the polynomial. How do you numerically compute the roots of a polynomial? Any guesses? There is a MATLAB function, but what does the MATLAB function do? How does the MATLAB compute the roots of a polynomial? An easy way is to take a matrix of superdiagonal ones and zeros everywhere else and put the coefficients of the characteristic polynomial in the last row. And then just take the eigenvalues of that matrix. So the eigenvalues of that matrix are the roots. This is, everybody with me on this? See, these are all the reasons you should never do math in PowerPoint. But today will be the only time we'll do it. So you put 0, 1, 1, 1. And then you just put minus C1, minus C2, minus Cn zeros here. And the eigenvalues of this matrix are B1, B2, Bn. Why is that? Because, if you wrote the characteristic polynomial of this matrix, determinant of Si minus A, it would be x to the power n plus C1 x to the power n minus 1, etc., etc. C1 is the sum of the eigenvalues. C2 is the product of the eigenvalues taken two at a time, etc., etc. Okay, so the reason that the numerical analysts, the Jim Demmels of the world, will complain because there's a famous example which says that if you take a matrix like that, and if all its entries were 0, the eigenvalues of this matrix were just at 0. But if you put a small epsilon perturbation, the eigenvalues are all the nth roots of, they're all the 1 over nth roots of epsilon multiplied by the n of them. So it's the spectral pattern corresponding to k equals 0, 1, 2, up to n minus 1. So those will be the n eigenvalues of this. And the problem is, even if epsilon were 10 to the minus n, which is presumably a small entry, then epsilon to the power 1 over n would still be 0.1, which could be a substantive entry. So, the computation of the eigenvalues of matrices like this are, is likely to be ill-posed. So MATLAB doesn't exactly do this. MATLAB does some clever hacks on top of, but the general idea is you can convert root finding into finding the eigenvalues of a matrix. That's sort of so it's a souped-up version of what I wrote here. Now, in our case, you should say, well, so it's easy for me to say the cluster centers are the roots of P and X. But, if somebody gave you a polynomial, a matrix like this, the odds are that the roots that you'll get for these polynomials are complex, because small amounts of noise will provide, will knock you out and sort of knock you out of the reals. Whereas you really want these cluster points to be real numbers, B1, B2, Bn are real. So, numerically, so even though it's okay to say this conceptually, numerically there are real issues with that one statement which says the cluster centers are the roots of Pn of x. But, the cluster centers are fine. But conceptually it's the whole answer. Solution is unique if there are at least as many points as there are groups. You have to have at least one point per cluster, otherwise you're out of business. And the solution is in closed form. You can find the roots of polynomials of degree 4 or less in closed form. Beyond degree 4, you're on your own. There's no closed form roots, and that's just a mathematical nicety. But already with this, you can use this to segment data. So how do you use this to segment data? If these were grayscale images, what you do is you convert them into long vectors, which vectors corresponding to the intensity values of all the pixels, and then you try to cluster them. And if you cluster them into 3 groups, what the groups are called, you call them black, gray, and white, comes out naturally from applying these the kind of algorithms that we said. I'm going to do the details a little bit later, but just to show you what happens, if you were to try to do this, and this is the original picture. If you used k-means, this is sort of what it does, is to break it up into black, the part of the image that was black. In this case, the part of the image that was black will now appear white out here, because those correspond to the ones, and the other parts correspond to zeros. The gray, so it's all of the background. That's what the black group is. The gray group is, of course, the stuff which is not white, which is, the white stuff is, of course, this person trying to throw the ball, and this person that's trying to reach the base here. And this last picture tells you what happens when you add them back on, and you see, because of noise and so on, what you add back on isn't exactly what you started with. And this is sort of what you get from the first two, are what you get from k-means and expectation maximization, whereas this technique that I told you about, this polynomial segmentation, which is what I just saw you do, is comparable. In detail, it does somewhat better at places close to the person's fingers and so on and so forth. But they're all sort of roughly comparable. The difference, of course, is that they're really fast. Expectation maximization, a wonderful crank. If you don't know better, that's just, that's the first thing you do when you want to write a paper and your deadline's tomorrow. But, it takes a long time. These problems are very non-convex. And, it really depends how you initialize it if you want it to converge to a local minimum. If you start doing it on more complicated images, so this is these two penguins talking to each other. And, this is what k-means does, that's what EM does, and this is what the polynomial segmentation does. If you use the polynomial segment, and this tells you what you get by putting everything back together. If you add black, gray, and white. Yeah, so white here is actually the white part of the penguin, the fronts of the penguins as well as the eyes. And the last picture tells you sort of the sum of all of those. So it tells you how much of the picture is actually retained by doing that. If you use the polynomial segmentation as the initial guess for k-means, or as the initial guess for EM, you can further refine it. And the biggest single advantage, of course, is that it's really fast. Because the numerics, I sort of made fun of the numerics, but these can actually be souped up, and they can all be converted into MATLAB code, which runs reasonably fast. And so I will cover this in some greater detail in terms of. And so in this thing we check we call this polynomial factorization, because this was really, we converted it to a 1D problem. It really is a considerable speed up over execution times for, so PS stands for the polynomial factorization, and if you use that as the initial guess for doing k-means, then k-means actually sharpens up the images, and that's sort of why we started paying attention to this. Amazingly, though, also that even though this, I'm going to redo, of course, the scalar, even the scalar calculation on the board next time, just because once you've really understood the scalar case, the generalization to higher dimensions is amazingly not difficult. It's really a question of lining up the notation to do it right. So let me just give you a preview of how you do it. That was scalar. So now we're going to enter the domain of multivariate. So how do you parameterize a plane? You know, in a multiple, in a dimension, in a hyperplane, when you talk about a capital D dimensional space, a hyperplane means that one dimension lower than the dimension of the ambient space. That's capital D minus 1. When that happens, the way you parameterize a hyperplane is by the normal vector. There's always a unique normal vector associated with the subspace. And if it was in 3 dimensions, you know, this is what this picture is like. The way you represent a subspace of dimension 2 in R3 is by a single normal, which is B transpose X equals 0. And this vector B is considered the normal to the subspace. Look, and I've written this in R3, but this could really be X belonging to R capital D, which is the dimension of the data. And B transpose X equals 0. It's a single scalar equation. And B, the coordinates of B are the coordinates of the normal. So every hyperplane has got one normal. Now in R2, how do you represent a line? The way you represent a line, one way to represent a line is by writing it as the intersection of 2 subspaces. I've written it as the intersection of 2 orthogonal subspaces. Subspaces need not be orthogonal. But once you have, let's stick to these orthogonal subspaces, you say that X belongs to the intersection of these 2 subspaces if it satisfies B1 transpose X equals 0, corresponding to subspace 1, and B2 transpose X equals 0. You know, the logical connective OR translates into a multiplication. Therefore, and there's no choice. You know, there's no easy way. You can say it's B1 transpose X times B2 transpose X equals 0. There's a separate constraint for each one of the normals. So the number of normals is called the codimension of the subspace. So a line has codimension 2, which means its dimension is 2 less than the dimension of the ambient space, and so there's 2 constraints. So the number of normals is the dimension of the space minus the dimension of the subspace. That's called the codimension of the space. So any subspace can be represented by a set of linear equations, B transpose X equals 0. So the representation of subspaces is as a set of polynomials of degree 1. And how many one subspace corresponds to, depending on its codimension, it tells you how many polynomials there are. So if you're told that you're given data that lives on either this space, either this plane or that plane, these are the yellow and black dots, you know, if it were to lie on this light green subspace or the steel colored space, that would correspond to B2 transpose X equals 0. If it were to belong to the green subspace, that's B1 transpose X equals 0. And the OR connective would now translate into B1 transpose times B2 transpose X equals 0. So it suddenly becomes a quadratic, because the quadratic, it becomes quadratic because there are 2 subspaces. Each subspace has just linear equations, but because when you have 2 subspaces, this connective OR makes it a a quadratic equation. If you were told that the data lies either on this red subspace here, or this, I guess this is still the teal subspace, or on this yellow line, how would you then parameterize it? Well, the plane again corresponds to B transpose X equals 0. The line corresponds to B1 transpose X equals 0 and B2 transpose X equals 0. So how do you then say it lies either on S1 or S2? You know, how do you say S1 union S2? You say B transpose X equals 0 or B1 transpose X equals 0 and B2 and I've written and as B1 transpose X equals B2 transpose X equals 0. So how does this connective OR factor through this? It says that S1 union S2 says, so the AND, because of B1 transpose and B2 transpose, is preserved, but the OR enables you to factor these through, and it says B transpose X times B1 transpose X equals 0, and B transpose X times B2 transpose X equals 0. So, the difference between this case and the case that was just before it is that the number of subspaces tells you whether it's a quadratic. You can imagine that if there were 3 subspaces, there'll be cubics. If there are n subspaces, there'll be n-ary equations. So the dimension of the vanishing polynomials is the number of subspaces, whereas whether it's quadratic or cubic depends on the codimensions of the subspaces. So in this case, this is codimension 2 and codimension 1. So the number of equations that you get is the product of those codimensions, 2 and 1. So that's why there's 2 equations here. So that's why it says that a union of n subspaces can be represented by a set of homogeneous polynomials. So what does does everybody know homogeneous? Homogeneous means that if you look at every term and you add up the powers of x, of all the components of x that show up in it, it's the same number. So for instance, if you have polynomials in x and y of order n, you have x to the power n minus 1 times y, and x to the power n minus 2 times y squared. The sum of the powers adds up to n. That's what homogeneous polynomials mean. Homogeneous polynomials means that the powers of all the components adds up to the same number. And the reason that's the case is because, all the entries are exactly quadratic in x. There are no linear entries in x, and there are no cubic entries in x. And that's why there are homogeneous degrees of polynomial n. And so how do you represent these? How do you represent these homogeneous polynomials? If you have a homogeneous polynomial in 2 variables, then, and if it's just x1 and x, if it was an R2 and x with x1 and x2, all the possible things that you can get in terms of homogeneous polynomials are x1 squared, x1, x2, and x2 squared. And that is why, these Veronese things that you talked about, Alan talked about, which I will also talk about, really correspond to all the homogeneous polynomials of order n. So in this particular case, if the ambient dimension was 2, and you were looking at all homogeneous polynomials of order 2 in 2 variables, you'd have x1 squared, x1, x2, and x2 squared. And k was 2. This 2 stands for the homogeneous polynomial of order 2. And this formula, which Alan was asked you to verify as homework, says that, how do you figure out how many coefficients there are? It's easy. You have k variables, and you can choose n out of them. Those are n balls. And if you work out the combinatorics, you get this formula, n plus k minus 1, choose n. Or you could do n plus k minus 1, choose k minus 1. And you get the same answer regardless. Yeah, there's one out there, yeah. So that tells you how many polynomials there are. And so, really, if you... I see. You're all done? Don't take the eraser because okay. Oh, okay, there are more erasers here. I guess you could have the eraser too. It's okay. Thank you. Yeah. So so the reason this Veronese map shows, so this is a fancy way of giving the relationship between the coefficients of B as a symmetric tensor corresponding to the symmetric tensor product of B1, B2. So look, I said it's not a good idea to digest math on PowerPoint. I'm going to do this by hand. This is just to show you that it's just a question of algebra, And the reason this Kernel PCA shows up, you see, at heart, what it's trying to do is even though you're trying to figure out how many subspaces there are, and you know, what does this correspond to? This corresponds to the fact that data lies either on subspace S1 with normal B1 or on subspace S2 with normal B2. If there were 3 subspaces, you'd have B1 transpose X times B2 transpose X times B3 transpose X equals 0. And you'd have all the cubic polynomials. In this case, the ambient dimension, capital K, would be 3. And, you know, you'd have to grind it out in terms of what this is. But, you know, this is not, when it comes time to mechanize all this, the linear algebra does not care about x1 squared, x1, x2, etc. Because, what, you know, all you care are the coefficients that multiply them. And that's a linear algebra calculation. That's an eigenvalue calculation. But in effect, what it does is, at the price of increasing this dimension, it makes it a linear problem. And it does suffer from some of the things that I told you, which are a bad idea. You know, you're linearly parametrizing these things by polynomials. You know, you're taking polynomials, and C1, C2, C3 are the coefficient of polynomials. You might wish to do other things with them. You know, when I taught the course in Stockholm, I remember the very first class. Oh, I see, we're past time. Okay, when I taught the course in Stockholm, you know, this one guy who had been working for what's a Swedish truck company? You know, Volvo. That's it. So, and you know, they'd been wanting to take measurements out of the GPS in these trucks and sort of fit the roads, you know, with the slope of the roads and so on and so forth. And he immediately went home and said, boy, I really need to take all this GPS data and fit it with polynomials. And he got terrible results. And he said, you know, this theory is terrible. It doesn't work. But, you know, the reason it didn't work is because, you know, some of his units were kilometers, whereas, you know, because that's the length of the road, whereas the elevation changes were in tens and hundreds of meters at best. So, you know, if the data is poorly conditioned, then somehow, you know, so you had height measurements in meters and length measurements in thousands of meters. So some of the entries were thousands, others were linear. And by the time he sort of multiplied x1 squared and x1, x2, you know, all the numerics all got shot to hell. So one caveat that I think hasn't made it into these notes is really that when it comes time to apply these methods, you have to have a sense that all these coefficients, x1, x2, x3, are all roughly normalized, you know, in the sense that you can't measure things in very different units to put them together. All right. So, you know, we will resume. I think I'll go back to the blackboard. And are people going to be upset to not have PowerPoint? The notes are all available, and there is PowerPoint. But I think we can make the PowerPoint available and write on the PowerPoint, and I'll work on the board. So maybe that's what we'll do. I'll certainly post today's notes. Okay, so thank you very much, and we'll see you. Hey, I think, though, that if the class continues to be small, I think that what we'll do is we'll convert it to not being a class, but really be a study group.